All right, here we go again. Let's get started on 4B. Okay, so this is our continuation of 4A, obviously, and we're looking at applications of derivatives, mainly in economics, but in other fields as well. And so we'll be introducing a lot of important new results in part 4B. And there will be a part 4C coming up. So let's get started with this. So first we start with the mean value theorem. Now, several of these theorems are very important for deriving results, but they're not necessarily useful for developing practical results. But it's important to understand how these theorems work because it helps us understand the concepts that we're doing in the chapter. So sometimes they're more practical than others, but they're always important for understanding how calculus works and where the results are actually coming from, because we don't always spend that much time understanding where the techniques come from. That has to wait till a class like real analysis, where you start to really focus on the foundations of calculus. And in a course like that, you actually spend a lot of time proving your results. Here, we're really more interested in learning the concepts and then applying them to real world situations. Anyway, so we also closely related here, we have this notion of Raleigh's theorem. Get this straightened out. All right, hold on one second. This is not my normal computer, as you can tell. I'm trying to set it up so that you can see everything. See, for whatever reason, it's kind of okay. That should do it. That should do it. Okay. So Raleigh's theorem tells us that if the values of a function are equal at the endpoints of an interval, then somewhere in between there has to be a point in the interval where f prime of c is 0. Okay. In other words, if we have oh, here we go. Here's some graphs that show us how this works. So we'll start with the one on the far left. And actually, let me do this. All right. So in other words, if you look in the one on the far left, at point A, B, and C, at point A and at point C, B rather, the function has the same value. We don't know what it is, but whatever it is, f of A and f of B are equal to each other. And because this is a smooth continuous function, there must be a point C in between somewhere at which the function reaches a maximum or a minimum value. Okay, in other words, f prime of c is 0, which means the tangent line to the function at that point is flat or horizontal, which implies that it is either a maximum or a minimum. It could be a relative minimum, it could be a relative maximum, a global minimum, or a global maximum, but it has to be one of them. And all it takes, surprisingly enough, is that the value of the function at both endpoints is the same. Whatever it is, it doesn't matter. As long as it's the same, Raleigh's theorem tells us that a relative extremum or some kind of extremum must exist in that interval. The second diagram, you can see that, again, f of A and f of B are equal to each other. And that's why that top red line is there. And then the bottom red line is there to remind us that at point C, which is somewhere between A and B, the tangent line is flat, it's a horizontal line, and the slope is 0. Now, in the third case, we have a more interesting one because there's actually two interior points to that interval at which we have either a relative maximum or a relative minimum. So we can have more than one. In other words, Raleigh's theorem only guarantees one point in the interior of that interval will be an extremum, but here we can see that it's possible to have two or more for a function like that. So now, what is this going to get us? It just means that if you have a case like that, you may be finding it difficult to calculate the relative extrema, but you know that they exist. Knowing that they exist will be useful information because, it might be complicated to find them, but at least you know that they exist. All right, well, anyway, So here's an actual specific example. F of x is x squared plus 2x. So over the interval -2, 0, we're going to demonstrate that there must be a critical point C in between somewhere at which the function has a first derivative of 0. So if you evaluate f of a, when a equals -2, you'll end up with 0. If you do the same thing for 0, you'll end up again with 0. So therefore, in fact, let's see if we can draw this thing. Oh, it's already there. Okay, good. I did this in Symbolab already. So in other words, this is the function, and you can see it is a parabola where a is a positive value, so it's facing upward, and it crosses the horizontal axis at the points -2 and 0. At both points, f of -2, for example, is 0. F of 0 is 0, and that means we know somewhere in between here, there must be a point where we have an extremum of some kind, which means that in this case, -1 is our critical point. And at that point, we have a relative minimum. Okay, actually, in this case, it turns out to be a global minimum, but we know that it's an extremum of some kind. And then we knew that because of Raleigh's theorem. We have to find it ourselves, but we knew that it existed. And it's really that simple. Okay, I mean, you're making sure, though, the important detail is that the interval must be such that the function has the same value at both endpoints. Otherwise, there's no guarantee that we'll find that critical point in the middle. Okay, now the mean value theorem. Raleigh's theorem is a special case of the mean value theorem. Because with the mean value theorem, f of a and f of b are not required to equal each other. So basically what's happening differently here is that as long as the function is continuous and differentiable, then there must be a point interior to AB such that the tangent line isn't necessarily equal to 0, but it's parallel to a secant line that connects the two endpoints. So that's going to be easier to understand with a graph. So here, for example, we have the two endpoints A and B. And so the tangent line, as you can see, has the same slope as the tangent line going through A and B. And of course, that's all that it's telling us. Now, it doesn't have to be 0, as you can see, but we know that it must be equal. The slope must be equal to the tangent line through the points A and B. Okay, so this is the more formal way of expressing this. It means that as long as we have an open interval A and B, the function has to be continuous over the closed interval AB. It only has to be differentiable over the open interval AB, which means it doesn't have to be differentiable directly at points A and B, although it often is, it doesn't have to be. And if that's the case, then somewhere in that open interval, there must be a point where that has this slope. And that slope, as it turns out, is the slope of the secant, which we saw earlier in the course. We saw how to calculate the slope of a tangent and a secant. This is the slope of the secant that connects points A and B. Oh, here we go. A very good numerical example. F of x is the square root of x. And over the interval, the closed interval 0, 9, we're guaranteed that there's at least one C such that f prime of C equals f of 9 minus f of 0 over 9 minus 0. So when we plug those in, f of 9 is just 3 because the function is radical x. F of 0 is 0. A isn't 0, B is 9. As you can see, what it's just saying is that we're guaranteeing that somewhere in that interval is a tangent line whose slope is 1/3, because that is equal to the slope of the secant that connects points A and B. So let's see if we can, I don't know if I was able to find a graph for that. Oh, yes. This is where we look for that point. Okay, good. So let's say that we take this function, we take its first derivative, and remember, we're trying to find a point where the derivative has a slope of 1/3. So we're going to take this expression and set it equal to 1/3, and that should give us the value of x at which the slope is 1/3. Okay, so let's try that. So the function, remember, the derivative is 1 over 2 radical x. So the point we're evaluating it is x. So we replace all the x's with c's. We set that equal to the slope that we determined earlier. And so now it's a simple matter of solving for c. So when you go through all the calculations, you'll see that the point that we need is 9/4. And now, well, what it's telling you is that the slope of the tangent at that point is equal to the slope of the secant between the points 0 and 9. Okay, so that's what the theorem is telling us. Not only does the point exist, but we can easily find out where it is because we know what the slope has to be, because we have the formula for calculating slopes of secant lines. Anyway, now here's an important consequence of this, and this is really where it starts to really matter for our results. Under these conditions, again, if f of x is continuous and differentiable, continuous over the closed interval, differentiable over the open interval, then if the derivative is positive throughout the entire interval, the function must be increasing over that interval. If the derivative is negative for all x in that interval, f of x must be decreasing. Like you can see in this picture, you can see where the function is rising, f prime of x is positive. Where the function is dropping, f prime of x is negative. And then once again, as the function increases, f prime of x is positive. So in other words, this is how we can identify points where we are looking for a relative maximum or minimum. Remember, we had that test where we said one way to find out if a point is a relative maximum or minimum is to check the sign of the first derivative on either side of that point. If the derivative goes from positive to negative, that means we must be at a relative maximum. If the derivative goes from negative to positive, that means we must be at a relative minimum. So in other words, that test that we've been using to identify relative extrema is justified by this mean value theorem. Before, we didn't explain where it came from. We just said, well, this is how it works. But now with this mean value theorem, we can demonstrate why this actually works. Why is it that whenever we have a relative maximum, it must be the case that the first derivative rises from positive and then falls to negative, or if it's a relative minimum, we go the opposite direction. So now we know why this is working. Anyway, what we can also do is take a look. Oh, this is actually quite important. If you can see these different functions, what we've done is we've picked 2 points and solved for their slopes, or the sign of the first derivatives. And so the upper left-hand corner, the first function a, we find that the function is increasing. And furthermore, it's actually increasing at an increasing rate, although we don't need to know that right now. And you can see that no matter where we put the tangent line on that region of the function, the first derivative is always positive rather. Okay, in other words, no matter what point we choose between a and b, as if we calculate a tangent line, the slope will have to be positive because the function is increasing throughout the entire interval. In part B, it's the other way around. Okay. Well, actually, it isn't the other way around. Sorry, I'm looking at the wrong one. What's happening is that the second function, it's increasing, but if you notice, it's slowing down, so to speak. It's increasing at a decreasing rate. And yet, throughout the entire interval, no matter where we choose to draw a tangent line, the first derivative has to be positive. Okay. On the left, the slopes are actually increasing. They're positive and increasing as we go from left to right. On the right-hand side, in diagram B, the slopes are positive throughout, but they are decreasing, going from a larger positive value to a smaller positive value. Now, later on, we'll see that we can capture this behavior with the second derivative. But for our purposes right now, all we need to know is that if the function is continuously increasing, the first derivative has to be positive throughout. And then in the bottom, you can see the opposite case. If it's the case that the first derivative is negative as we go from a to b, that means the function must be decreasing. Okay, and you can see again, there's two different ways it can decrease. In the first case, it's decreasing at an increasing rate. And in the second case, it's decreasing at a decreasing rate. But any way you look at it, we can tell from the sign of the first derivative throughout that interval, what is the behavior of the function? And again, this is a direct consequence of the mean value theorem. And this is one of the reasons why it's so useful, because then we can develop general rules that enable us to identify regions where the function is increasing and decreasing. Okay, so in other words, in math, everything is done very formally. We have to have results that let us prove that what we're doing is correct. We can't just say, well, you know, it looks right. That doesn't cut it in math. We have to have a formal way of proving that what we're doing is correct. That's what theorems are for. It basically sets a guideline that lets you find the results you're looking for, but it also sets up the foundation for developing more advanced results. All right. Now, by the way, it doesn't show it here, but at some point, if the function reaches a point where the tangent is 0, that means it's about to switch from increasing to decreasing or decreasing to increasing. Hello.
Hi, everyone is like that.
Yeah, so I was getting a little work. Everybody was good. Thank you. Okay. Yes, now here you can see what's happening, and this is, we have some very bizarre regions along here. You can go see, like in point A, the derivative is actually undefined there. And yet we know that this is a relative maximum because the sign of the first derivative is switching from positive to negative. That's all we need. In part B, you can see that the sign is switching from negative to positive. And so therefore, B turns out to be a relative minimum. And from that point on, the function is increasing. As we go to C, the tangent line has a slope of 0. But if you notice, it's not a relative maximum or minimum because the sign of the first derivative remains positive, which implies that the function is increasing continuously, and therefore it cannot be either a relative maximum or minimum. And then for part D, we do in fact have a relative maximum. You can see the sign of the first derivative is, ooh, it looks like they've got a typo in this diagram. The section after D clearly has a negative first derivative, so that's a typo there. I didn't notice that before. Oops, I'll have to write to the author of the book. So that's how we know that this is a relative maximum, because we went from positive to negative. The function is going from increasing to decreasing. All right, anyway. The first derivative test. Now, another option we have when looking for relative extrema is not to look at the signs of the first derivative, but what we're going to do, oh my God, look at this one. What we're going to do is identify the points where the first derivative is actually equal to 0. Okay, so in other words, the points where the first derivative is actually 0 are guaranteed to be relative maxima or minima. We can still check the sign on either side, but either one of two things can be done. We can check the signs on either side, or as it turns out later on, we'll introduce the second derivative test where we only need the first and second derivative at the critical points. So let's just take a quick look at this one again. We've got a cubic equation, which looks like this. And you can see clearly that there's a couple of places where we have clearly a relative maximum and minimum. But let's find them the formal way instead of looking at the graph. So we'll take the first derivative and using the power rule, you can see that this is now 3x squared. This is minus 6x. This is minus 9. Of course, don't forget, we're using the power rule here. And Now, this time we can simplify it by dividing out both sides by 3. And then we can factor it out. As it turns out, it's a relatively straightforward factoring problem. And it turns out that we have x minus 3 times x plus 1 equals 0. And therefore, we set them both equal to 0 individually, and we find that the 2 points we're looking for are 3 and -1. So let's look at the graph for a second. So this is our -1, and this is 3. Okay, so now the question is whether each one, now without the graph, it would be hard to say whether these are relative maxima or minima. So we still have to test to see which one it is. So we divide the function into these 3 intervals, and we're going to check out the sign. What we can do is pick any random point in these intervals and evaluate the first derivative at that point, and then see what their sign is, of course. We don't really care what the derivative is. We only care about the sign. So in the first interval, I chose -2. And that f prime of -2, that is positive. Okay, so that is pretty much what you would have expected. Let's go back to the graph. Then in the next interval, between -1 and 3, I chose -2, and I ended up with 5, which is positive. Oh, sorry, I'm looking at the wrong one. The second one, I chose 0, and f prime of 0 is -3. And then, of course, as you can probably guess, what's coming next is that the next region will be positive. Well, let's prove it. And again, you only have to pick one random point in there between 3 and infinity. That would be 4. I chose 4, and that gave me 5, which is clearly positive. Let's fill that in. So anyway, so I summarized these here. In the first interval, we have f prime of x is positive, then we go to negative, then positive, which implies that -1, f, whatever the point is, we're going from positive to negative, which means we have a relative maximum. And then negative to positive means it's a relative minimum. And that's exactly what the graph shows us. So the graph just confirms what we've already discovered. Okay, so f prime of -1, let's see. So then I solved them. So the first one is -1, 4. Okay, so this is -1, 4. So the 4 is the actual relative maximum. In other words, the function reaches a relatively maximum value at that point. Eventually, it will go up higher than that, but in this immediate area, the function will not rise above 4. Okay, now for the other point that we have here, when you evaluate this function at that point, where f of 3, that is, it turns out that f of 3 is -28. There we go, 3 comma. This point is 3 -28. So -28 is the smallest value the function will assume within that interval. It is smaller down here, of course, but only within this immediate range, the function will not fall below -28. Okay, so we get the two relative maxima, relative extrema, relative maximum, relative minimum, and we're able to identify them using the so-called first derivative test, where we simply need to know what is the sign of the first derivative on either side of each critical point. Okay, so these are in fact critical points because that's the point where the first derivative is actually equal to 0. So this way we can identify the ranges within this function where it's increasing and decreasing and where the relative extrema occur. All right. Now, concavity, points of inflection. Now we're starting to need the second derivative. What happens here is that the concavity is essentially describing the rate of change of the first derivative. All right. So the way to think about this is that if the first derivative is increasing, not just positive, but increasing throughout the entire interval, f of x is said to be concave up. If f prime of x, the first derivative, is decreasing throughout the interval, f of x is said to be concave down. So again, we're describing the rate of change of the first derivative. Okay, now, so I borrowed these from the book, and you can see, and these are the same basic graphs we had earlier. Here, f prime of x is always positive, but if we go from left to right, it's getting bigger. In other words, yes, of course, it's positive throughout, but as we move from A to B, the first derivative is getting larger, more positive, I guess we could think of it. So we said earlier that the function is increasing at an increasing rate. And more formally, that means the function is concave up. Over here on the right, even though, again, f prime of x is positive, if you notice as we go from A to B, it's getting smaller. Okay, the curve is getting flatter. So in other words, you can think of that as increasing at a decreasing rate. And more formally, we say that the function is concave down within that range. And by the way, I'll just give you a helpful hint where this is going. When it's concave up, that implies that the second derivative is positive. And concave down implies that the second derivative is negative. Because the second derivative describes the rate of change of the first derivative. So if the first derivative is increasing, the second derivative must be positive. If the first derivative is decreasing, the sign is irrelevant for this. If it's decreasing, the second derivative is negative. Okay. Now down at the bottom, this function is decreasing, but the rate of decrease is slowing down. In other words, it's like a car rolling down a hill, and then it sort of slows down as it gets to the bottom. The derivative, in spite of the fact that it's negative, it's getting less negative as we go from A to B. Okay, so in other words, let's say it goes from -3 to -1. Well, even though they're both negative numbers, that means that the slope is actually going up. And we also describe that as concave up, which once again implies the second derivative is positive. And finally, in this last case, the function is decreasing at an increasing rate. The first derivative is negative, and it's getting more negative as we go down from A to B. And that tells me that this function is concave down, which implies that the second derivative is negative because of the fact that the first derivative is getting smaller, or in this case, more negative. So that's what concavity is all about. It's essentially showing us what is happening to the first derivative. Is it increasing or is it decreasing, regardless of whether it's positive or negative? Now, by the way, you can think of this in terms of geometry too. I drew a couple of sketches in here. Concave up means, let me just remind us that this is concave up. If you notice, I've drawn a secant line through two endpoints. And if you notice, the secant line between those 2 points is always greater than the function. That tells me that in terms of geometry, this must be a concave up function, which again implies that the second derivative is positive. All right, so in other words, you can check just visually looking at the graph. And again, if a secant line is always above the function throughout that interval, A to B, then that implies a concave up function, or think of it as a positive second derivative. Well, then in this case, it's just the other way around. This is concave down. Meaning we have a negative second derivative, which implies essentially that the first derivative is decreasing. In the first graph, it is positive but shrinking, so to speak, the first derivative. In the second case, it is going from a small negative number to a larger negative number. But either way, the secant line, as you can see, is everywhere below the curve at that in that interval. And that's another way to tell that the function is concave down. Now, what about the points of inflection? What is that all about? Before we get to that, we can test for concavity. And again, it just comes down to the sign of the second derivative. Now, if you notice, we are assuming that the functions we're looking at can be differentiated twice. In other words, both the first and second derivatives exist. Otherwise, we can't do this. And it really only has to be over that interval. It doesn't have to be for the entire function. So as long as this first derivative is positive for all x's in that interval, then f of x is concave up, as we've seen. If f prime, double prime of x is negative for all x in that interval, then f of x is concave down. And again, you can tell by looking at them. Concave up means the first derivative is rising. Concave down means it's shrinking. Okay, either it's becoming less positive or more negative. Okay, now, inflection points. Now, sometimes a function, the same function, can have regions within which it is concave up and regions within which it is concave down. The point at which the second derivative switches from one to the other is called an inflection point. So, like here, for example, although it may not be obvious right off the bat, but if you look carefully as we go from left to right, the first derivative is going from negative to positive up to point A. There's a relative minimum here at point C in the middle. But because the slope is going from negative to positive, that means it's increasing. The slope is increasing. And that implies a positive second derivative, which means the function is within this range, concave up. Then when we get past point A, the opposite happens. The slope goes from positive to negative, which implies that it's shrinking, and the second derivative is negative. And that implies that it's concave down. So the point where this changes is right here. That is our inflection point. Okay, so that's what it means. Where does it switch from concave up to down? Or it could also be concave down to up. Okay, so let's do a specific example. Here's a function. It's a polynomial. We know that it is differentiable twice. And we're going to see if we can identify. By the way, just because it's a polynomial, there's no guarantee that an inflection point exists. But if it's there, we can find it by taking the first and second derivatives and observing the values in those different intervals. So here it is. You can see the inflection point is going to be roughly right about here. Okay, you can tell because the slopes are slowly decreasing, and then all of a sudden they're increasing. Okay. So that roughly should be where we find our inflection point. Well, let's prove it. Oh, by the way, one more thing we have to be aware of. It turns out that concavity can switch not just when f double prime is 0, but it turns out that if it is undefined at any points, that also can be a point where the concavity switches. We're not going to see that here because, of course, it's a polynomial. But in more advanced functions, this could actually happen. Okay, so the concavity, what we need to check for is any points where the second derivative is 0, but also if there might be any points where the second derivative is undefined. So we'll just go ahead and find the first and second derivatives using the power rule. And what do we do first? Well, we need to know where does the second derivative equal 0, if anywhere. Well, this is a pretty straightforward one. We have 6x minus 12. Set that equal to 0, x equals 2. All right, let's look at the graph again and see. Yeah, that looks about right. This is 2. Yes. So we're going to test the sign of this second derivative over the two intervals. Now, like I said, what we're going to discover is that the slope is decreasing, which implies it'll be negative here. It should be positive here. And exactly 0 here. And so let's just confirm that. Well, actually, we just proved that it's equal to 0 here. So it's just a question now of finding what's going on either side. All right. Hold on a second. Okay, so why don't we check out the second? Well, first, we have two intervals and we need to consider negative infinity up to 2, 2 up to infinity. So we can pick any random point in those intervals and check out the sign of the second derivative. Remember, the second derivative is 6x minus 12. So in the interval negative infinity to 2, we can just easily pick 0, and you can see that that is in fact negative 12. It is negative as we predicted. Let's go back up here. By the way, if you wanted to, you could go back and check the first derivatives as well, just to confirm this. It isn't really necessary though. For this, our purposes here, we're only really interested in the second derivative. And then we go into the interval from 2 to infinity to see what's going on there. And I picked 3. I just randomly picked 3. It is positive. F double prime of 3 is 6. That's a positive second derivative as we expected. So because it switched from concave down to up, due to this, and you can tell because of the sign, in this interval, F double prime is negative. And over here, F double prime is positive. That indicates that where x equals 2, that is where our inflection point is. So I plugged it into the function, and it turns out that the value that we actually have here is 2, 32. That is our inflection point. So let's see. Yeah, you know, sometimes these symbol lab graphs, like here, you notice it jumps right up to 20. So that looks about right, 32. So this is what we're aiming for, 2, 32. That's our inflection point. And again, you know, there's no guarantee that it exists in the first place, but with polynomials in particular, especially higher order polynomials, that you normally do get an inflection point, at least one. All right. So, so anyway, what this leads us up to is that we can use this second derivative test. Instead of checking the sign of the first derivative near each critical point to identify extrema, what we can do instead is say, well, listen, first we find the critical point where f prime of c is 0, okay, which means the tangent line is flat. Assuming the function is continuous over the interval containing that point, all we need to know is at that critical point, if the second derivative is positive, then f of x is a minimum. if f double prime of x is negative, at that point, then we have a maximum. And if f double prime of c is 0, then the test is inconclusive, which means we have to try something different. All right. And by the way, that something different turns out to be, as we'll see later on, you can try then the so-called third derivative test. And if that is inconclusive, you can try the fourth and the fifth. Eventually, you will come up with a result. So let's check it out with this function. All right, we're going to find all the local extrema with this very high order polynomial. So I'm dying to see what this graph looks like. Oh, well, it's a little weird. When, you know, you can clearly see that we have a relative maximum, a relative minimum. This is one of those points where the slope of the tangent line will be flat, but yet it is neither a relative extreme or relative, sorry, it was neither a relative minimum or maximum. It is neither. Okay, and of course we already knew that that could happen. So why don't we take the first two derivatives using the power rule, and we find, first we need to know where the critical values are. That comes from the first derivative being equal to 0. In other words, the points where we have a flat tangent line, so there's 3 of them, as you can see, and those points are, well, we have to be clever here. We have to set this equal to 0, and you can see such a high order equation, there could potentially be up to 4 solutions here. Well, there isn't. So we ended up with 0, radical 3, and radical negative 3, which radical 3 is approximately 1.73. So let's go back and look at our graph. So that part is accomplished. Those are our 3 critical points that are potentially relative extrema. Now let's prove it. So what we're going to do is we're going to evaluate the second derivative of the 3 points. This is different than what we've done before. Before we checked out the signs of the first derivative on either side. So like this first one, you can see it's a relative maximum because we're going to go from a positive first derivative to a negative. For radical 3 down here, it's the other way around. But at 0, if you notice, the first derivative stays positive on either side, which is how we know that it is neither a relative maximum nor a relative minimum. But here, we're going to use the second derivative. So it saves us the trouble of calculating the first derivative on either side. In other words, we only need to do one calculation and evaluate it. So when x equals 0, the second derivative, so this is something we should not be surprised by. The second derivative test is inconclusive because clearly this is not an extreme point. Okay, so it's going to say, well, it's, you know, it doesn't work here. It's the second derivative is 0. So then you would actually have to continue testing to find out what's going on here. We'll see more of that later on. Now, on either side, starting with the negative radical 3, the second derivative turns out to be negative, which is exactly what we would have expected. And you can see that that implies f double prime of x is negative. And the reason why that's happening is because the first derivative is decreasing on either side of it. Specifically, it's going from positive to negative. Okay, but that means it is a relative maximum. With this one, we have the 0, and then when we go to positive radical 3, we do have, in fact, a positive second derivative, which is no surprise because you can see the first derivative is going from negative to positive. So in other words, f prime of x is increasing. When we get to that point, which implies a positive second derivative, which implies in turn a relative minimum point. Okay, so you can see what's happening here. By the second derivative being positive means that the first derivative is going from, in this case, it's increasing from negative to positive. So it avoids the need to calculate the first derivative on either side of the point. We can go directly to the second derivative and just determine what its sign is, and that's all we need. Okay, so of course you do have to calculate a second derivative, so you're not saving that much work, but still, it is maybe a little bit quicker. But we do have to be careful about the cases where we have the inconclusive test. The first derivative test, we would have known right away that this is not an extreme point because the first derivative is positive throughout. All right, so I summarized these below, and you can see the results of the test, and we were able to identify these points from the second derivative, but it's important to understand what that's telling us about the first derivatives too. Okay. All right. So that was a lot of fun. Now that proves to be a very important set of results, because this is later on when we start doing optimization, where we're trying to figure out the maximum or minimum value of a function. Let's say, for example, we're trying to figure out if a particular output for a company is maximizing their profits. This is exactly the technique that we can use to find out if a point of production is either a maximum or a minimum or possibly neither. And so this way it avoids the need to always draw graphs of these functions. We can just go directly to the second derivative and figure out what's going on with this point at which we're producing. So we'll definitely have some examples of that. So, you know, this is, like I was saying before, the mean value theorem is very abstract and theoretical, but we do need it to help us justify these results. But once that's done, well, it turns out that what we just did here is actually very applicable in a lot of disciplines. And so any area where we might need to optimize a function, this is very, very important information. Okay, so anyway, so it looks like this is it for 4B. So soon enough, we'll be doing 4C, and we'll take it from there. So I guess I'll see you next time.